In this video, you will learn how the Radiosity lighting model works and how it's best utilized for pre-lights. You will also learn about scenarios where Radiosity can be overkill and not really provide any benefit to the pre-light. To some, Radiosity may seem like the final boss in the game, while pre-lighting without Radiosity is just one of his minions. However, that is not entirely correct. To start off, it's important to know the difference between pre-lighting with and without Radiosity. Radiosity is an advanced lighting model which can be used with the old scanline renderer. It is a physically accurate lighting model, which is able to calculate indirect light rays for your lights. You might be wondering what indirect illumination is all about. By default, without Radiosity, when adding pre-light in 3ds Max, it only calculates direct light rays. That means it's only the polygons that are seen by the light which will end up being illuminated. The polygons that are not seen by a light source will be pitch black. To resolve this, we have two options. We could add a gray base layer to our vertex colors or use a skylight to bring in global illumination. But this produces flat lighting because it just adds a flat color. It can work fine, but if it's a more complex scene with many objects that are occluding light, such as a city or interior with many props, then we would want to use Radiosity instead. So, we now know that the old scanline renderer only calculates direct light rays and leaves unseen polygons pitch black. In real life, there's a term called light bounces. Light bounces is what's responsible for indirect illumination. To test this, we'll start off with a very basic scene. Start by creating a box. The scale doesn't matter as we're just testing, but scale does matter for production, because a box the size of a stadium is going to be lit differently than a box the size of your room. Therefore, the lighting values shown in this guide will be different for you if your values and scale settings are different. I'll invert the box normals and enable backface culling so that I can see into the box. I'll create a second box right through the center. The height and width doesn't really matter. I'll give them both a gray wire color. The light source will be a photometric free light. I could as well have created a standard Omni light like in previous guides. But standard lights do not work well with Radiosity because they use a different light model. Photometric lights are the most optimized for Radiosity. If we created a daylight system, then we would also have to select the IES sky and sun lights instead of the standard variants. I'll place the light near the intersecting box. This way the light should be casting light on the large box, but the intersecting box would end up occluding most of the light, which prevents the box from being illuminated evenly. I want to see how the light looks, and so I'll enable lighting in viewport. It's going to be very faint because it isn't bright enough. I'll first set my exposure control as physical with the 8 key. I could lower the exposure value to get better lighting, but I'd prefer changing the light strength itself. Due to the scale of this box, you may need a strength of 1,000 or even in the millions. You could avoid such high values by tweaking your exposure control though. To better illustrate the power of Radiosity, I'll limit my light range to just a small distance from the light itself. Once it looks good in viewport, we need to ensure that our model has enough vertices for Radiosity to calculate a good pre-light. We could also use the Radiosity meshing options, which adaptively subdivides the mesh where there is light detail and then save the subdivision using a plugin, but this collapses our modifiers, which is not ideal. I'll bring up the Radiosity interface. You will notice it has a lot of settings, but for now, we only really need to worry about the Radiosity processing parameters rollout. Radiosity processing times can vary between computers and scene complexities. For a scene like this, we shouldn't have to worry about processing times. But as a rule of thumb, you should keep settings low while testing Radiosity solution. I'll set the quality as 25. This is the initial quality before additional resampling is applied to the Radiosity solution. I'll keep refine iterations as 0. These are the second quality settings we can use to improve the accuracy of our lighting, at the expense of longer calculation times. I'll keep the filtering as 0. These filters work by blurring indirect and direct light rays, which can help prevent artifacts that would normally be present in a Radiosity lighting solution. If you have tried using Blur Brush and Vertex Paint Modifier, this works similarly to these filters. In the rendering parameters, I'll enable Reuse Direct Illumination from Radiosity solution. Enabling this setting is only necessary if you plan on testing your Radiosity with rendering, but I'll just test it in viewport for the most part. With the settings configured, press Start. You'll notice that the entire room is mostly lit, even though the original light source only reached a small portion of the model. You'll also notice that both sides of the intersecting box is illuminated. This was made possible by our indirect light rays, which keep bouncing onto different surfaces and reflecting light onto other surfaces. The basics of light bounces doesn't just end there. If we now set the intersecting box as red color and restart the Radiosity solution, the entire room will be faintly colored red. The reason the room is faint red is because our light source casts direct rays onto both the gray box and the red box. When the direct light rays hit those two surfaces, the direct light rays then bounce off in all directions and generates indirect light rays when they hit other surfaces. When these indirect light rays bounces like a bouncing ball, they inherit the color of the surface they land on. In our case, the light rays hit both the red polygons and the gray polygons, and therefore cast a mix of gray and red light onto surrounding polygons many times. This not only globally illuminates our model, but also casts multiple colors of light all around the model. The lighting might look okay in viewport, but it is not very accurate at this time. If you press F3, you will notice there aren't enough vertices in the model to prevent light bleeding artifacts. You can prevent some light bleeding issues by cutting in some edge loops where the intersecting wall is located. If I press Start again, the accuracy is somewhat improved, but is still far from perfect. I could raise the initial quality and refine iterations to production level, but that wouldn't resolve the artifacts either. I'll therefore have to raise the subdivisions in the model. I'll reduce the subdivision size to 10% and see how that looks. Now we're getting a more accurate lighting solution, except there's a bunch of light splotches all over the model. This is where our quality refinement settings come into play. A high initial quality setting can work for some, but it can be incredibly taxing on some computers and scenes. We can choose between 3 quality settings: the initial quality, which can be incredibly slow, the refine iterations, which can also be slow, and filtering, which can be faster. But because it blurs the lighting, it may not be favorable for some. I'll set filtering to a value of 2. You can't really say it looks fantastic, but this is after all an unrealistic scene. Normally you would not light a model like this. There would be more lights in the scene, and ideally they would be in the ceiling instead of above the floor. I'll assign the lighting solution to vertex colors now. Whether you set it as lighting only or lighting and diffuse depends on the type of model you're pre-lighting. I'll set it as lighting and diffuse. If we now assign vertex colors without radiosity, we can compare between pre-light made with radiosity and without radiosity. Even though this is an edge case scenario, we can definitely call the radiosity variant the winner for its accuracy. One last thing we can do is set the exposure value to 5 instead of 6, and then recalculate radiosity. This should result in much better results because we're making the lighting just a tad brighter. With this test done, you should have the basic knowledge of how Radiosity works. We'll now move on to more practical tests with GTA models, similarly to what was done with the previous video, where we went over the basics of pre-lighting with a few different case scenarios. For the test with GTA models, there are a few more notes to keep in mind when using Radiosity. The original game model pre-lights are often very washed out, meaning there isn't much contrast in the lighting. The highlights are often subtle and blend softly into the midtones. The shadows and midtones also blend softly together. Therefore, we should do the same to our pre-light. Instead of having a high contrast lighting with deep shadows, mixed midtones, and sharp illuminating highlights, we need to keep average the shadows, midtones, and highlights. Many models in the game also have an issue with overlapping or duplicated inverted faces. These are very problematic when using Radiosity, and so unfortunately there is some mesh cleanup that we need to do before we can finish our Radiosity pre-light. GTA buildings were originally exported without vertex normals, meaning the original smooth and hard shading that Rockstar used when pre-lighting their models is now gone. That means we will need to adjust the smoothing groups of models ourselves. When using Radiosity for projects that have several individual objects in the scene, instead of one combined mesh, you will experience visible seams in the pre-light. The indirect and direct light filtering also works best with combined meshes. It's therefore recommended that when working with Radiosity, you merge all objects as one mesh. Alternatively, you can opt for Weighted Normals modifier or the Edit Normals modifier to try and tackle shading issues that may occur in the Radiosity solution. With these issues out of the way, let's begin. If you are on 3ds Max 2025 or newer, please download the Fixed Goldfish's scripts from his release page. Otherwise, you will experience errors when importing and exporting IPL files. Import the LAE2 IPL maps into 3ds Max. These models will be used to test Radiosity, but you can follow along just fine with your own models. I'll replace all scene assets with assets that were imported with the Heroes plugin. I recommend you also do this for best results, but it is not mandatory. Follow guide ID 86 on how to set up a scene that contains all DFF models imported by the Heroes plugin. If you don't want to go through the setup, you could as well convert scene materials to RW materials. For that, head into Utility tab, click Max Script, click GTA Helper, then select Cam to RW materials. This will give you better material display in viewport, but the mesh errors will remain unless you set it up the same way I have. The imported lights can be useful for calculating nighttime lighting, but I won't be showing how to do nighttime lighting in this video, and so I'll just remove all lights from scene. Disable textures in viewport and display scene lighting in viewport. Create a daylight system and accept the exposure control prompt. The height of the daylight system doesn't matter. Set the lights as IES type, as these are the most optimized for Radiosity. The next few parameters that I'll be changing in exposure control and in the daylight system are really just optional. I strongly recommend tweaking them to your liking. They are more like a post-processing effect to create a more GTA-style lighting, but are definitely not required to get a good-looking pre-light. So please, do not stress over the various settings that I'm adjusting in this video. For the exposure control, I'll set it as an EV of 16. This makes the lighting a bit darker. Set midtones as 3. This helps create a washed out look, which is similar to that seen in original game models. The final result won't be this bright though. Before calculating radiosity, it's important to remember that having this many models in the scene will make it slow to process. I'll therefore delete the objects I won't need. Deleting this many objects can take a few minutes due to them storing selection sets. Alternatively, you could disable their radiosity flag in object settings. If you experience sluggish viewport, try saving your scene, close 3ds Max, start it again, and reopen the scene. In Radiosity settings, set the quality as 85 and refine iterations as 10. These are just reference values. You are welcome to change depending on how fast you want the calculation to be. It can also help to just play around with the values to see how each affect the lighting calculation in your own scene. In Radiosity meshing parameters, set it to include skylight. Start the radiosity calculation. If you are getting missing textures error, simply press X, search Asset, and click Remove Missing Assets. Then click Start Again. If you find it takes too long to process, try reducing the quality and refine iterations. You'll notice that even though our lighting was very washed out and mostly white, with Radiosity, it has now regained a lot of contrast, and I think the shadows are too strong. When working with maps, or incomplete maps such as the one we are working with here, it can help to create a gray plane below the map for casting light bounces back onto the map. As shown earlier in the video, if we made the plane red, then it would be reflecting red light rays back onto the models. If we make the plane white, then it will be like placing the sun 1 kilometer away from Earth, which is not ideal. The changes may be hardly visible, but we can always adjust the color later by assigning a material to the plane if we want to tweak it. I'll select a few models and try assigning radiosity to vertex colors. As a final touch, I find tweaking the levels helps create better prelight. You might find this lighting to work fine, but there are a few obvious errors in the lighting solution, and so I'll disable vertex colors in viewport and delete the vertex paint modifiers. The first issue is the sewage structure has a very dark shadow. The direction of the light and the intersecting geometry causes this. For this reason, I'll start off manually adjusting the daylight placement. Try starting the radiosity solution again and configure your vertex paint modifier accordingly. The lighting has definitely improved, but it's not quite there yet. The reason you are seeing artifacts and bad shading is due to the hard and smooth shading used on the models. As explained earlier, we need to set the smoothing groups ourselves to better determine how lighting is cast on the surfaces. Also, the reason some objects have oddly shaded triangulation is due to overlapping, flipped faces in the meshes as explained earlier. To resolve this, we need to remove the overlapping faces, which can be quite time-consuming. I have not yet tested if this is a problem in-game, or if it's just because you cannot enable backface culling in viewport while models are shaded in vertex colors. Therefore, I advise testing your pre-lit model in-game before cleaning up the flipped faces. This walkthrough should hopefully help you master your Radiosity skills. Please keep in mind that the workflow and values can be adjusted to your liking, and what is shown in the video is not a definitive perfect solution.